Welcome to Spring LIB.
So here we're trying to calculate the kinetic energy of a person running, and we'll calculate the total energy the from running, the kinetic energy translational, and then the rotational kinetic energy from his legs and his arms. So we have the runner is running at 12 kilometers per hour. We can convert this 1,000 meters for every kilometer. Then we have 1 hour for every 3,600 seconds. This is giving us 3.333 meters per second. So that's the velocity of the runner. And then we have angular displacement. It's going to be plus or minus 30 degrees. Plus or minus 30 degrees every 5 seconds, 0.5 seconds rather, half a second. We have the length of the arms is 70 centimeters or 0.7 meters. We have the length of the legs is 90 centimeters or 0.9 meters. And then we have theta, which in this case, because it's plus or minus 30 degrees in half a second, we're going to say 60 degrees, and we'll say pi radian for every 180 degrees. And this is going to be pi 3 radian rather we can say pi over 3 radian, and then we can say delta t equals 0.5 seconds. At this point, they want us to find the average angular velocity. So for A, we'll have omega equaling the angular displacement divided by delta t. So this is going to be pi over 3 times 1 over 0.5, and this is going to be equal to 2.10 radians per second. So this will be your answer for A. And then for B, they want us to find the total rotational energy. So we have to find the kinetic energy, the rotational kinetic energy from the arms plus the rotational kinetic energy from the legs, add them up and to find the sum, and that will give us the total rotational energy. So we have the mass of the arms is going to be 13% of the mass of the runner himself. So this is going to be 75 kilograms. So the mass of the arms is 9.75 kilograms. Mass of the legs is going to be 37% of the mass of the runner. So this will be 27.75 kilograms. And at this point, we can say that the moments of inertia of the arms about the shoulder would be I sub a, and we can say m sub a L sub a squared divided by 3. So that would be for the arms, and then for the legs, we have m sub L sub L squared over 3. So this would be the moment of inertia of the arms about the shoulder, and then these would be the moment of inertia of the legs about the hips. And so here we can say that the kinetic energy rotational of the arms is going to be equal to 1 over 2 times MA LA squared over 3 times omega squared, given that the rotational kinetic energy is half I omega squared. And then we can solve and say that this is going to be equal to mass of the arms times the length of the arms squared times omega squared all over 6. We can then say that the kinetic energy rotational of the legs is going to be the exact same thing. Mass of the legs, length of the legs squared, omega squared all over 6. And at this point, we can say that the rotational energy total will be equal to the rotational kinetic energy of the arms plus the rotational kinetic energy of the legs. And this is going to be omega squared times the mass of the arms, length of the arms squared, plus the mass of the legs, length of the legs squared, all divided by 6. So that would be the total, and then we can then solve for this and say 2.10 squared, and then the mass of the arms, 9.75, the length of the arms, 0.7 squared, plus 27.75 times the length of the legs squared, all divided by 6, and this is going to equal 20.032 joules. For part C, we can find the translational kinetic energy of the runner. So this is going to simply be mv squared over 2. So this would be 75 times 3.333 squared, all divided by 2, and this is going to equal 416.667 joules. And then part D asks us to find the percentage of the rotational energy in terms of the total energy. So we can define a variable F. This is going to be RE total, the total rotational energy, divided by the total energy, and this is going to be 20.032 joules divided by 416.667 plus 20.032, and this is going to equal, we're going to multiply this by 100%, and this is going to equal 4.587%. So the total, so 4.587% of the total energy is rotational energy. The rest, overwhelmingly, is translational kinetic energy. So over 95% of the total energy comes from the translational energy of the runner rather than the rotational energy of the runner's legs and the runner's arms. And that's the end of the solution. Thank you for watching.